Okay, hey there folks, this is Dr. Schultz, and in today's video lesson we are going to introduce the concept of acceleration. I'm going to start off by defining acceleration in words, and then what we'll do is we'll take a look at an example of acceleration that we hear about in advertising probably all the time. We'll look at some numbers, we'll introduce a formula, and we'll wrap up by talking about the difference between average acceleration and instantaneous acceleration. And hopefully a lot of what we're going to say in this video is going to be familiar to you. So let's start off with a word definition for acceleration. I'll say it first and then I'll write it down. Acceleration is the change in an object's velocity over time. Sorry about that. Okay, so I'll read that again. It's the definition of acceleration is that it is the change in an object's velocity over time. Now, let's think of an example here from advertising. And I'm going to say the example first, the way that oftentimes you hear it in commercials, and then we're going to write down what it really means and figure out what the advertiser is selling you. So here's the advertisement. Sometimes if you watch television or listen to the radio, you might hear advertisements for new cars. And the advertisement, somewhere in the ad, it might say something like this. They might say, the new model X5T Lexus can do 0 to 60 in 4. Okay? Actually, it's not the best in the world, but it goes something like that. So I'll repeat that again. This new model of car can do 0 to 60 in 4. Okay, so the question is what does that really mean? And if you drive, you probably know what that means. The 0 to 60 means miles per hour. It's referring to your starting and your stopping speeds, your ending speeds. So 0 miles per hour to 60 miles per hour. Why do they pick those two speeds? Because maybe you are accelerating from a rest position and you're trying to get onto the expressway. How about the 4? If they say that you do 0 to 60 in 4, well, that's going to refer most likely to seconds. So the fact that you can accelerate from rest to 60 miles per hour in 4 seconds is basically a measurement of how powerful the engine is of the car. Now, like I said, that's actually not very good these days. Probably a good muscle car is going to get you from 0 to 60 in like 2.8 or something like that. But we're going to use 4 here just for the example. So you could say I'm going to say Lexus, but this is really not an endorsement of Lexus here. The Lexus does 0 miles per hour to 60 miles per hour in 4 seconds. I'll put that in quotes because that's what you might hear. So the question is what are they really selling you here? Are they selling you the idea that the Lexus can drive at 60 miles per hour? I don't think so. A Lexus can go much faster than that. My minivan can easily do 60 miles per hour at home. So what they're not really selling you like velocity, right? Because most cars can do 60 miles per hour. It's not a problem. But what they're selling you is actually the fact that it can go from not moving to traveling at that speed in a certain amount of time. Okay. Now that is acceleration. Okay. Acceleration is a change in an object's velocity over time. Here's your change in velocity right here. That's your delta V. Remember that symbol delta? That means a change in velocity. That's a change of plus 60 miles per hour. And here is the time part. That's your t. And so you're saying that can happen in that period of time. So we're going to define acceleration now with a formula that matches up the words. And the formula, we're going to say this is average acceleration. It's going to be defined as the change in velocity divided by time. And it's that simple. Okay. Because you're looking at the change in velocity over time. If you want to, you can even write this differently. You should know that change in velocity would mean final velocity minus initial velocity. And usually the time interval we can just write as t. Sometimes it's written as delta t. Okay. This definition is a lot like the definition that we gave for average velocity. Remember, if you take the a away and you make this average velocity, then you have a change in position over time. So that would be delta x over t. So that was something that we started off in this course. So average acceleration is a lot like that. Okay. Let's plug in the numbers from the commercial here to make this crystal clear. The change in velocity is going to be v final, which is 60 miles per hour, minus the initial velocity of 0 miles per hour, and that's happening in 4 seconds. If you do the math on this, you get 60 minus 0 divided by 4, it's 15, right? And the units are a little bit weird. It's miles per hour. On top, those units stay because you're just subtracting two measurements. And then you still have to divide by seconds. Okay, and the seconds don't cancel out anything. The seconds don't cancel out the hours. Now you might be thinking, well, that's just because seconds need to be converted into hours. And that's actually, you could do that, but they're still not going to cancel out. Okay, you're always going to end up with speed units on top divided by time units, and the time units do not cancel out. If you're wondering about the algebra of that, I'm going to write this in a slightly different way. I'm going to say that it's 15 miles per hours times seconds, right? Because you've got seconds in the denominator and you've got hours in the denominator, and they both kind of they multiply by each other. And so the dimensions here are sort of different. The dimensions are going to be length divided by time squared. You know what that means? It's because we have time multiplied by time. And so the times do not cancel out, but they give you time squared. So acceleration is always going to have units that are like this. Now, we're not going to usually kind of use miles, and we don't like to typically use different units for time. So more typical units in this physics class are going to be kind of the metric units that we like, and more typical are going to be meters, and then we'll put both the time units in seconds, and so it'll be meters per second squared. Okay, and those are going to be kind of our typical units that we use in class. You could go back to this example with the Lexus, and you could convert 60 miles per hour into meters per second. So you would have, so many meters per second minus so many meters per second, divide by so many seconds. All right, that simplifies to meters per second over seconds. And then these seconds jump up and multiply, and so you end up with meters per second squared. And so that's how that would work for many of the examples that we're going to do. Okay. All right, so that's basically kind of the overall, the word definition of acceleration, followed by a formula definition of average acceleration, followed by an example with numbers plugging in. Now, one last thing about this. Let's go back to the example of the Lexus. Okay, and I'm going to make two tables here. And my tables are going to be tables maybe that one of the test engineers would use when they were testing out the new Lexus. So someone is out on a track, and they're going to measure the velocity of the Lexus as it starts from rest. And they're going to measure it every 1 second. So this column here is going to be kind of like these are going to be instantaneous velocities. All right, instantaneous. So someone's looking at the speedometer of the car as time goes on. So you're going to want to look at the time at the speed at 0 seconds, at 1, 2, 3, and 4. Okay, and that obviously would be some data that you would have to measure. Now we already know for this Lexus, I'm going to put this up here, that the acceleration, the average acceleration, is 15 miles per hour per second. Okay, and we kind of know that the car starts from rest, and we know that after 4 seconds it ends up with a speed of 60 miles per hour. Okay, and the question is how does it get there, right? It's kind of the in-between part. How do you go from 0 to 60 miles per hour? Do you go up evenly or not? And the answer is kind of it depends. Okay, in like a car, like an actual vehicle, let's say that an engineer measures the velocities. Okay, let's take these numbers. Okay, let's say that they get at 1 second speed of 30 miles per hour. At 2 seconds a speed of 45 miles per hour. At 3 seconds a speed of 55 miles per hour. And finally at 4 seconds a speed of 60 miles per hour. Alright, if you look at this, you can tell, I hope you can tell that the speeds are not increasing evenly. Okay, when you go from here to here, you've added 30 miles per hour. Alright, that's a lot. When you go from 30 to 45, you've only added 15. When you go from 45 to 55, you've only added 10. And from 55 to 60, you've only added 5. This is kind of reality. Okay, this type of acceleration is not steady. This would be called non-constant acceleration because it has uneven changes in velocity, uneven delta V's for equal time intervals. Right? The time intervals are always 1 second. So, but you can tell that the velocity is not changing the same. Well, why is that? That's because in a car, there's a transmission, and the transmission doesn't work perfectly smoothly. It doesn't always give you the same increase in speed. The transmission is a complicated machine, and it happens to work that way. Okay, so the most general type of acceleration that can happen here is that this is happening, where it's not constant. Okay, we will find though in many examples in physics that you can have accelerations which are constant. Okay, which are constants. So let's take a look at this again, and let's predict what they would be if you had a constant acceleration. What would that look like? Okay, so we're going to put our times in of 0, 1, 2, 3, and 4 seconds. And again, you know that the car starts at rest and it ends at 60. Now, how would the speed have to increase to go from 0 to 60 in a constant or an even way? And the answer would be, it's actually kind of coming from the acceleration that we figured out. Let's have it add 15 miles per hour on every second. So it would start at 0, it goes to 15, then it goes to 30, then it goes to 45. Sorry about that. And then it goes to 60. So if you look at this, we're going up in nice steps of 15. So that's plus 15, this is plus 15, plus 15, plus 15. That's basically a constant acceleration, right? Sometimes that's also called a uniform acceleration. Okay, and cars don't usually do this. Okay, However, one big example of something that does it would be objects which are in free fall. So freely falling objects. All right, something that you just drop and there's not a lot of air resistance. They are going to follow this type of a pattern. Also, objects on ramps. Typically, if there's not a lot of friction, are going to accelerate in kind of a constant sort of a way like this. So obviously those are really important in physics, those two examples. You know, we're going to focus on those in a few days. Okay. So kind of to come back to the idea here, these two examples, if you look at them, non-constant acceleration versus constant acceleration, it's kind of a lot like when we talked about velocity changing or velocity being constant. Remember when you did the physics behind the wheel lab, and basically your instantaneous speed was changing minute by minute? Okay, that's kind of what was happening with our velocities here, and that means that the acceleration is constantly changing. And so if you say that the acceleration is 15 miles per hour per second, that's really just an average. But your instantaneous acceleration is not going to necessarily be equal to the average, right? I'll say they're not equal necessarily. They might be, but in general they're not going to be, because the acceleration could be plus 30, plus 15, plus 10, whatever. Now, if you're nice and even Steven, or nice and steady, that's different. And this is the case where you have uniform or constant acceleration. And for constant acceleration, your instantaneous acceleration is always equal to the average. And in this case, in this example, it's always equal to 15 miles per hour per second. So if in this example, it's 15 miles per hour per second. Okay. By the way, that's a different way of writing it. It's kind of weird, but miles per hour per second. I just want you to see several ways of writing it. So in conclusion, you know, these two ways of accelerating are very much like what we talked about with ways that, you know, you can change your position if you're driving on a trip. You know, your velocities can be changing all the time, but you can always talk about an average velocity. Okay, that would be this case. Or you could be driving with it with a constant velocity, and in which case your velocity is always the exact same value, and it will be equal to the average for the whole interval. Okay? All right. Last thing, we'll just say something about this, is that acceleration is a vector quantity. Okay? And I hope by now you're probably like, yay, acceleration has direction, because that's what vectors have. And that's totally it. Okay? So, for example, to make a connection to the lab that you did, if you have a ramp and you put a ball on it, let's assume that the ball starts maybe up here and it starts to roll down the ramp. Okay? So after some time has gone by, that ball has a velocity which is in the direction of going down the ramp. Now, you guys know that the ball is going to speed up. It's going to change its velocity. It's going to increase its velocity in the positive direction. And what we would say in that case would be that the acceleration is actually its own vector, and it's pointing in the same direction as the velocity. And so this causes the object to speed up. Okay? Because these two vectors are basically going in the same direction. And that's always true. Whenever the acceleration and the velocity go together, things are going to speed up. And that can happen in a lot of different ways. If the velocity is going to the left and the acceleration is going to the left, it's also going to speed up. If the velocity is going down, the acceleration is going down, you're also going to speed up. You can have a lot of different combinations as long as the two vectors are going in the same direction, that you're going to get speeding up. Now, if you go the other way, let's say that the marble is rolling uphill, okay, but it's slowing down as it goes. Okay, so it's moving up, but you know that as things go uphill, they slow down. Well, in this particular case, the acceleration is heading the opposite way. And that's a recipe for a slowdown. And that happens whenever acceleration vectors point in the opposite direction of the object's instantaneous velocity. So right here, the object happens to be moving up, but it's accelerating down. And you can imagine a lot of different situations where this might happen, wherever you have opposite vectors here. So one thing that's important is that you don't confuse acceleration and velocity vectors. They're not the same thing. They don't even have to be going in the same direction necessarily. Okay, they are up here when the object is speeding up, but if they're going in opposite directions, they cause something to slow down, and that's completely okay. All right. We'll talk about examples like if you throw a ball up into the air and the ball is moving up. Well, while it's moving up, it's accelerating down at the same time. It's crazy. And so if the velocity is up and the acceleration is down, that means you're going to be slowing down. And that's exactly what the ball does on its way up. Okay. So we're going to talk some more about this tomorrow. I hope this helps you a little bit with the analysis that you're going to do tonight of your lab data. When you finish up, so tonight, I'll just say a couple things. Finish the marble analysis. Okay, finish that tonight. The instructions are online. I do want you to sketch some motion diagrams. I think that you guys are getting the idea that if the marble is rolling downhill, that it starts off here, and it starts off kind of slow. But as time goes on, it's going further and further. So what I really want you guys to get out of from your data tonight is make this your t is equal to 0. This next point would be the 1/4 time. This is the 1/2 time. This is the 3/4 time. This is the full time. And I want you to actually calculate these distances. These are the interval distances. So that's going to be your delta x's in centimeters. And then for each of those intervals, you're also going to find the velocity in centimeters per second, because you're going to take that interval displacement in centimeters, and you're going to divide it by the 1/4 time that you figured out from your data. So do that tonight. It's really important you complete that in your lab notebooks. Make the sketch, complete the tables, answer the question, and tomorrow we can look at data and see where we are in things. Okay? All right, cool. Then we'll see you guys tomorrow.